Yeah, a lot of people still joining. I think we're gonna kick it off though. Hopefully folks won't miss too much. So welcome to the presentation. Today's seminar is titled Demystifying Artificial Intelligence. This webinar is going to be recorded, and remember there's a Q&A feature, so you can submit those Q&As as they come, or those questions as they come up, and we'll get to them later. And this presentation is brought to you by Akur8. It's the Akur8 Academy series.
Yeah. So I know working with Max, we were going to be able to put a lot into this presentation. So like you said, the title is Demystifying Artificial Intelligence, but take a look at this subtitle, Dispelling Myths and Identifying Transformative Applications in Actuarial Work. We'll touch more on this subtitle a little bit later, but we have a lot we're going to discuss during today's webinar.
And as Josh said, my name is Max. I'm an actuarial data scientist here at Akur8. I work out of the US branch, and so does Josh. Josh is a fellow of the Casualty Actuarial Society and accompanies me on the ADS team here at Akur8.
So why are we all here today? I think you know AI is a big topic. Just look at NVIDIA's stock price this year alone. The moment of time we're in is often called the AI boom, or others are calling it the AI spring. Now, there's some debate about when this started, 2014 with Google's acquisition of DeepMind, 2016 with AlphaGo, but for the general public, AI really started to boom in 2021 through 2023, with generative AI and applications like ChatGPT really starting to take off.
And we'd say, take all the perspectives that you've seen on artificial intelligence over the past year or so and reduce them to a single dimension. And so I'd argue that on that dimension, you'd probably have two ends of the spectrum that would be very opposing, but equally disenfranchised on this topic. So one side is that AI skeptic who, really disenfranchised, think this is a lot of hype and not a lot of substance. And on the other end, you have that AI fanatic. So I think everyone knows someone like this, that person who, really only wants to talk about it if it's cutting edge, that digital pulsing brain. Otherwise, they're not interested in it. And so when Josh mentioned that subtitle, I think that was our concern, is that that subtitle was so strong on this presentation that we might kind of, disenfranchise these folks further, but we really wanted to cater to the middle in this presentation.
Max originally gave this presentation at the Casualty Actuarial Society, who's our preferred partner for putting out research here in the US. And the CAS recently put out a call for essays, exploring the intersection of actuarial science and artificial intelligence. And we really like this pragmatic approach of how we can blend AI into actuarial science. And this is the tone we hope to strike in this presentation. That is, there are practical ways for us as actuaries to utilize AI.
And as Josh said, we give a lot of research that we present with the Casualty Actuarial Society in the US. And the question is this artificial intelligence? Is it machine learning? And I think, depending on how you define these things, you could come to either conclusion, but I'd argue that it's really proper machine learning. So most people agree that machine learning is a subset of the class that we call artificial intelligence. And a lot of the things that we do in actuarial science are in that machine learning field, but they're the complement of deep learning. I have a little bit of a love-hate relationship with these Venn diagrams. They're, definitionally correct. But they can be very rigid, and we'll see an example of that later. I'll note that, if you want to go viral, post one of these things on LinkedIn, people eat these up. But we're actually going to see a lot of these Venn diagrams throughout this presentation.
So what are we going to talk about today? I want to zoom out and talk about artificial intelligence as a whole. We want to talk about things like neuroscience, philosophy, economics, computer science, and argue that artificial intelligence is a domain that intersects with these domains, their intersections, and expands even further. Now, don't read too much into this as we put it together rather quickly. And I think these Venn diagrams can be a little too rigid for what we'll be talking about conceptually.
And if you think our Venn diagrams are sprawling, I'd say that they can get even more sprawling than that. So we're going to reference this web series on reinforcement by David Silver later on. He's one of the co-founders of Google DeepMind before it was acquired by Google. And you can see he was just talking specifically on reinforcement learning, and these Venn diagrams can get very sprawling. So stick with us. You'll see them a bunch throughout here, but remember to abstract these ideas. Now, Josh mentioned that we gave this presentation before at the spring meeting. And when I first gave it, I was a little hesitant when I reread that subtitle. But then I went back and I reread my synopsis that I submitted. And I noticed that I said we were going to demystify artificial intelligence by clarifying that at its core, it's a collection of sophisticated algorithms. Now, I stand by this, but I think in retrospect, this was a little bit too reductive. Because think about the ghosts in something like Pac-Man. Most people would say these ghosts are governed by artificial intelligence, but they're not all that sophisticated of algorithms. They're actually pretty simple. And it's not so much that they're algorithmic, right? Because Euclid's division algorithm is probably an equally sophisticated algorithm, but most people wouldn't call that artificial intelligence. So what's really the difference between these two?
Now I have some definitions for you. We know everyone loves definition slides, forgive us, but we're going to make a point with this. So I'm going to read these out loud. IBM says, artificial intelligence is a technology that enables computers and machines to simulate human intelligence and problem-solving capabilities. Stanford University says the science and engineering of making intelligent machines. And then McKinsey & Company says artificial intelligence is a machine's ability to perform some cognitive functions we usually associate with human minds. Now, I assume everyone listening to this is human, and humans are really good at finding patterns. I'm going to help you see a few patterns in these definitions. In all of these, we're talking about machines and computers, and we're trying to get them to do something human, particularly things like intelligence, cognitions, references to our minds. Now, this discussion points to the Turing test. As you read and listen to material about artificial intelligence, the Turing test is often brought up as a measure of artificial intelligence. In this test, both a human and a computer are asked to submit a response to questions. And if a human evaluator cannot reliably distinguish between the response of the machine and the response of the computer, the human, then the machine is considered to have passed the test. Now, there's been a lot of debate around this test. Should the test be 2 minutes long or 2 hours long? Should it cover basic life experiences or technical topics? Is this even a good measure of intelligence?
And what this is really getting at is a lot of the philosophical debate in the class of artificial intelligence. So this was very heated in the 80s and 90s. This was maybe the primary focus as computing power started to grow quickly. And my favorite living mathematician, Roger Penrose, was very active in the debate, so much so that he authored 2 books on this, which are still in the conversation today. And I haven't read these books from cover to cover, but I posted some of his lectures on these books on my LinkedIn, and I encourage you to check it out. Now, Roger Penrose kind of had a bit of a contrarian view on the topic, and he argued that human cognition is not inherently algorithmic, and therefore, computationally, you cannot just recreate what we have. What we have is special. And he also argued that human cognition is a quantum phenomena, which is a little bit above my pay grade, but interesting nonetheless.
Yeah, I think all this is really interesting. I also think it's potentially distracting, right? Does it matter if we synthetically create something akin to cognition with algorithms? Why does it need to be human? What if in some aspects it is better or different? Now, we have largely moved on from these debates, but as DeepMind started having these major breakthroughs, there was a resurfacing discussion around the singularity. That is, if AI could build new AI, which could then in turn build better AI, which could in turn build even smarter AI, you reach the singularity, where AI becomes more intelligent than humans. There was a lot of fanaticism, a lot of fear-mongering around this, but as we see now, it didn't live up to the hype. AI can perform better than humans in specific domains, but we haven't yet reached artificial general intelligence, where an AI system can perform better than a human across a wide variety of domains and tasks. But again, something interesting to bring up in an AI presentation, especially as organizations and governments are grappling with how to move forward within this AI boom.
So I want to present to you a strange photo of a man holding a textbook, but it happens to be a very important textbook. It's titled Artificial Intelligence, A Modern Approach, and it's the 4th edition. This is the authoritative textbook on artificial intelligence. So if you take a first semester or second semester course, I'm almost certain you're going to get assigned this book. And this book is so influential that it has a cult following. People are taking pictures with it. And yes, I consider this a flex. But the reason we bring this up and we built up all those slides is to get to this definition. And this is what this textbook says the definition of artificial intelligence is. the study of agents that receive precepts from the environment and perform actions. We really like this definition, and this is the one that we'll be using throughout this presentation, and we hope you adopt. We've dropped the baggage of the human element, and we've got a functional definition that really helps us understand why the ghosts in Pac-Man are different from Euclid's algorithm. Now, I want to give a really brief history of artificial intelligence. Josh brought up the Turing test, and a lot of people say that's when the discipline of AI started, but you could really trace it back to very far back, maybe even Aristotle. This diagram that we have here starts in the 1600s with Pascal, who built a calculating machine. Some people say the next step was that Charles Babbage and Ada Lovelace built this programmable machine. They never finished it. It never came to fruition. But it's really interesting. Ada Lovelace actually created like the first software code before computers could even run. But as you fast forward, it took till the 1950s for things to really start heating up. And you can see from Alan Turing's Turing test, we started picking up some momentum, but it really wasn't until the 2000s. So zoom in a little bit further, and you can see, it was very slow in building up from that 1950s to those 2000s. And even more recently, almost all the contributions have been since the 2010s. You also see a reference to the AI winter here. We'll talk a little bit about that in deep learning. But I want to zoom in even further. This is a timeline of just 2023 for just generative AI, specifically just video. So this thing is moving really fast. Now, you might say on here, some of those things were product releases, but I'm going to argue that almost everything on this timeline came with a very significant contribution to what was already out there. So moving very fast at this time.
And it isn't slowing down. Now, I can't validate the truth to this chart, which was posted on Reddit, but what they're showing is that the number of publications related to machine learning and artificial intelligence has grown exponentially with a doubling rate of 24 months. Now, this chart ended in 2021, but from what we've seen, the patterns continued. It is rare for me to log on to LinkedIn without seeing someone reference a new paper in this field.
And these are not inconsequential papers. The week before we gave this presentation the first time, there was this huge paper that dropped about challenging the idea of the multi-layer perceptron in deep learning and totally uprooting everything that we had known about it. And it was kind of like the GAMS of deep learning. And so this is not unusual. Even since this paper came out, there's been some very consequential papers. So things are moving fast and they're very consequential.
But I don't think we need to get caught up in all the new stuff. In fact, in this presentation, we'll be giving an overview of the different eras of AI. Now, these aren't formalized. We're just using them for convenience. But right now, we're in the generative AI era. We'd say before this was the machine learning era. And this is where we saw a lot of advancements in our field, particularly advancements in GLMs. And then before this was the search era. Now, search is largely forgotten, but it was and is hugely consequential. Search is extremely useful, and for a long time was at the frontier of AI research.
So that's what we want to talk about first. We mentioned those AI textbooks earlier. If you open up an artificial intelligence textbook, I'm guessing the first few chapters are going to be on search because it is so foundational to the discipline. So what do we mean by search? So let's start with the most simple version of search, and this is called uninformed search. So we don't have a lot of information about the environment other than what we can interact with immediately. And so in this example, we have a bunch of treasure chests, and I'm going to take a young ACAS and I tell her, hey, you're an ACAS. If you want to become a fellow, just open these treasure chests up until you find a certificate, at which point you'll move right to fellowship. You don't have to take any exams. And she says, what's the catch? And you say, there's no catch. Just open the treasure chest. You have to close the lid when you're done. But once you find that certificate, you're a fellow. So she's smart. She starts in the top left. She goes the right, goes down a row up until she finds it, and she becomes a fellow. It was that easy. This is an example of uninformed search. Now, that situation was easy, but what about something like this? Now they take Max Martinelli, who's not credentialed, and they say, hey, Max, you want to be an ACAS? Go find the certificate. How are you going to do that in this situation? Because remember, you have to close the lid when you're done. You can't mark it, so you have to remember where you've been. So this is a much more challenging problem and requires a lot of memory.
So how do we use uninformed search to do this? Zooming out, the first step is to define some sort of path or graph. For example, we could specify which chest we would start with and build a path from there. That is, the chests closest to our starting point would be in the first layer of the graph, the chests closest to those would be in the second level, etc. Now, there are a few ways to approach this. Let's start on the left with depth first. It is memory inefficient, but it has a high variance time complexity, and an accountably infinite setting is potentially incomplete. You can get stuck in a rabbit hole. With this method, we're going to go all the way down the trees and then backtrack. So why is this useful? You only need to memorize or keep in memory wherever you need to backtrack to. The next method, shown on the right, is breadth first. Instead of going down each branch of the tree, the algorithm is first going to open the chests closest to the starting point, and then open the next layer of chests, and so forth. This method is highly memory inefficient, but it has a low variance time complexity, which means on average, it gets to the answer in the same amount of time. And the good news is it is complete in a countably infinite setting. There are elements to both these methods we like. The question is, can we do better?
And surprisingly, we can. There's actually a way to blend both of them and get the best of both worlds. So something that balances the trade-offs of these, and it's called iterative deepening search. As you can see by the diagram on the right, that it's kind of doing both. So as you see, we're mixing a little bit of breadth first and depth first, and we're still going to use a little bit more memory, but on average, it'll be much less, and we'll have something that's complete in a countably infinite setting, and going to have that inability to get stuck with the depth where you can keep going. So this is very useful, and this has actually been one of the significant innovations in search, that we can blend both of those things and not get something that's bad overall, but can improve on this.
So to illustrate this, let's say you have a 15 puzzle. Many of you have seen this before. To solve this puzzle, you move one piece at a time till all the pieces are ordered 1 through 15. If you were to code these methods up, you would see that iterative deepening really is the best of both worlds. But as we examine this problem, it looks a little different from the treasure chest problem. That is, we have a sense of how close we are to the solution. So we introduced the idea of an informed or heuristic search. Heuristic search was the workhorse of AI for many, many years. So how do we do this? We simply incorporate the idea of a heuristic, something that starts to formalize how close to the solution we are and prioritize paths we should search. But again, it doesn't have to be all that accurate. It could be as simple as how many pieces are in the right place. And you'd be amazed at how much this helps the problem and how well these algorithms can perform.
So Josh brought up maps earlier, and so let's look at an example with maps. When I first gave this presentation, it was at the spring meeting in Atlanta, and the question was, how would you develop an intelligent agent that's going to bring you from Atlanta to Phoenix, where the annual meeting is? That is, we don't want to explore paths that go through Chicago or Cancun, but we want to formalize this, and you'd be amazed how simple this is. We introduced the idea of the A-star algorithm. So the A-star algorithm, very simple, and Josh mentioned these simple heuristics really simplify the problem. All it is we're going to expand the paths based on the sum of their current path cost and an estimated cost to the target. That's it. If you develop an agent that does this, you'll never explore things like Chicago or Cancun, and it makes the problem go from intractable to actually very easy. And what's interesting is that estimated cost to get to the target doesn't have to be exact. It can literally just be a straight line, even if there's no road between the current path and the target. So something very simple makes this very tractable. And what's interesting is a mix of iterative deepening and A-star exists now, called iterative deepening A-star, and has become the modern workhorse of heuristic search. There's other types of searches for different problems. So maybe you've heard of Deep Blue, which was the chess playing AI from IBM. And in game settings, you're often playing against an adversary. And so the question is, how are we going to search through all the possible paths in something like chess when there's, tons of combinations? You'd need, decades and supercomputers that are very powerful to search all those things. How are we going to develop an agent that's going to work in that setting? And so in an adversarial setting, there's an idea of alpha beta pruning on the minimax algorithm. And the idea here is that I'm going to always try to maximize my score, and my opponent is always going to try to minimize my score. So I'm going to assume that I play rationally and my opponent plays rationally, and I'm never going to search the paths that don't support that. So I'm going to prune those out. And this makes something like chess, which is very difficult, become tractable. And we can now solve that game and be very, very smart. But what about something like this? So say that we work at an infrastructure consultancy and a client comes to us and they say, we need to lay some pipe through a marshland and we need your help designing this. You say, okay, how are we going to do it? They say, well, first we need to get from the bottom left corner to the top right corner, but we need to do so in a way that it minimizes costs. We say, okay, so what are the cost constraints here? They say, well, we prefer shorter distances to longer distances. Obviously, the pipe is expensive. We'd rather use less than more. So in this example, we'd rather have the green path than the red path. But it's not that easy. We have to avoid those green polygons. The green polygons represent the marshland, and you can go through them, but it's just way more expensive to put the pipe through that area. So you'd have to be very strategic with where you lay that pipe. The next is we also need to make sure that we don't have sharp elbow joints. They reduce the pressure in the pipe, so we'd prefer a smoother path to a coarser one. And so the question is, how are you going to do this? How are you going to use those algorithms on the prior pages to solve this problem? And it might be possible, but probably not. So we introduced the idea of genetic algorithms. So genetic algorithms is that we're going to take a population of individuals, and maybe we just start them randomly. But then we're going to take the best individuals from that population, and we're going to do some sort of crossover or maybe introduce some mutation. And so what you're looking at on the left is a whole bunch of random individuals. We're taking the top 5 from each population. Then we do some crossover and we continue this process for many generations. Now, the pros of something like genetic algorithms is that they're really robust, tend to get really good answers. They're very flexible. They can be applied to a ton of different situations. The cons are that it's computationally complex. So I let this run over my computer overnight. It takes a very long time. And it's not guaranteed to converge to a global minimum, but you can usually get a good answer. You can see around the 1700th generation, we actually kind of converge to something that looks really good. Probably matches your intuition. So let me display this side by side. You can see on the left, we have this, chaotic starting point that looks bonkers, but eventually we get to something that looks really good, and we've reduced the cost by like 85%. I will say that took 6 hours to code for just 2 minutes a slide. So we do this because I love you. But yes, it's kind of hard to go through those slides so quickly.
Yeah, definitely cool stuff. Okay, so that's search. Next thing we're going to talk about is rules-based AI. So when we originally put up the Pac-Man example, some of you might have thought, are those ghosts really AI? And we'd say yes, they are rules-based algorithms. Going back to our modern definition, the ghosts are agents monitoring the environment to perform action. The red ghost generally targets Pac-Man's current location. The pink ghost targets 4 spaces ahead of Pac-Man. They are monitoring the environment and responding accordingly.
If you don't think this is artificial intelligence, don't take our word for it. Google has some guidelines for using machine learning for their developers. And they make an argument that you shouldn't use machine learning unless you have to. Rules-based agents tend to be really good. But they also emphasize if you must use machine learning, don't do so until you have data. Because machine learning requires data, but these rules-based agents don't.
So now, rules-based AI and expert systems. The idea is that you know something about the world, and you can knowledge engineer that into an intelligent agent. These rules can be deterministic, or you can even program in some probabilistic behaviors if you want to be more stochastic. But it is these explicit rules, often in the form of if-then statements. Now, you might be looking at these textbooks and say, those look pretty old. And that one on the right even has a CD-ROM reference.
I think you'd be surprised to know that this type of agent lives on. So we present to you 2 more modern textbooks. First one is Artificial Intelligence for Games. And the author of this textbook makes a very compelling argument that rules-based agents tend to do very well and even outperform machine learning methods. And you might say, well, games aren't really applicable to what you do, but games have actually been the forefront of almost all the artificial intelligence innovations. So a lot of them start with games and then extend to other applications. Additionally, you see the textbook on reinforcement learning. Now, reinforcement learning is a form of machine learning. It requires data. But you'd be surprised if you read this textbook how much they reference optimal control theory. And the idea is that we've kind of moved our knowledge engineering from the agent to the rewards. So really interesting to see how this type of agent lives on. So why do we like these things? Well, the first is that they're really transparent. You know exactly why it did what it did without having to dig in. The transparency in these is very desirable. And for that same reason, it's very predictable. Again, as long as the environment stays relatively stable, you can expect what these things will do just by having them running. Now, that can backfire if you have something like COVID where auto frequency drops off a cliff. Maybe having this agent running with some of your prior assumptions isn't going to be a great idea. But nonetheless, this can be very good most of the time. The biggest advantage is no data required, right? So data is really expensive to procure, store, wrangle. And the idea that we know something about the world, we can engineer an agent that reflects that is a really desirable property. So now we move on to our next section, generalized linear models, GLMs. This is when we're giving this presentation live, we get to look around the room and we can usually tell who's the AI skeptic and who's the AI fanatic because it tends to infuriate both. The AI skeptic doesn't want to challenge the purity of their GLMs with this AI hype, and the AI fanatic just doesn't believe it's AI. I don't know where this misconception came from. Linear models and their variants, including generalized linear models, are indisputably artificial intelligence and machine learning. If you don't believe me, go reference any one of the top 5 textbooks in computer science on AI, ML, or even deep learning. So you can see that deep learning textbook has reference to GLMs or to linear models, and you'll see why in a few sections. It has this desirable property of transparency that is unrivaled in the machine learning field. I'll also mention that one on the right by Murphy, Machine Learning, has hundreds of pages on these different types of agents and a whole section on generalized linear models. Why do we like these things? So again, it's the transparency, but not just that. If you have a phenomena that you're modeling that follows the exponential dispersion family, these are really good tools. Now, the backstory is we started with things like linear regression, logistic regression, Poisson regression, each a different framework for a different topic. But then we had some geniuses figure out we can generalize this and abstract it into a single framework that unifies them all and has some additional properties that we like. We liked these methods so much that we started innovating on them and creating variants. So things like penalized regression and elastic net, as well as generalized additive models. So now we were doing things like automatic feature selection, but also automatic feature engineering. And we liked those so much that we continued to innovate on them and blend those things together. So now we have things that do both at the same time, like derivative lasso and AGLM. These are really powerful cutting edge machine learning techniques and very useful. They retain the transparency, but we can model those phenomena that follow the exponential dispersion family.
So let me take a minute to back up and talk about the no free lunch theorem. The no free lunch theorem, which actually isn't a theorem in machine learning, but technically it's from randomized optimization, states that without prior knowledge, no single algorithm could perform optimally across all possible problem domains or data sets. Okay, so why are we talking about this? This is a good thing to live by. If you are a machine learning engineer, the idea is you should try many different algorithms because some might be better suited to your problem than others. The problem is we are not machine learning engineers. We are not working without prior knowledge, and we are not working in all possible problem domains. Rather, we are typically working with the same types of data and the same types of problems we worked with last time. So we know something about the world. We know we're probably going to use GLMs or GBMs.
Now you might be asking, why are we bringing up GBMs in the GLM section? And again, we've given this presentation before. We've collected a little feedback. People thought we were a bit negative on the GBMs. I want to be crystal clear. Like GBMs, they're super cool. But we've been talking about fanaticism a lot in this presentation, and there is definitely some GBM fanaticism going on. I'm really active on LinkedIn. I see a lot of oversimplifications on GBMs that are evolving into myths. So I want to address a few of those in this section. So the first is that GLMs are primitive and they require manual feature engineering where GBMs are automatic. Now, that might have been true 15 years ago, but again, that suggests to me that someone is not using the modern variants. So again, things like derivative lasso and AGLM have all the things that we love about the GBM, the automatic feature engineering, the automatic feature selection, but we get to retain those features that we like the parameters. The next is that boosting never overfits and GBMs always outperform GLMs. Okay, so I have no idea where this one came from. GBMs are overfitting machines. And so you can see a whole bunch of references on the internet where people are talking about their GBMs are overfitting. every time I've ever built a GBM, the majority of my time is making sure that I didn't overfit. But the boosting part is actually important. So the magic of GBMs is not those shallow trees. It's the idea of the boosting. Boosting is the magic that makes these things so powerful. And if you ever read a machine learning book, I encourage you to go read about boosting. It's very cool. But again, to say that they always outperform the GLMs is not correct. And we see on average that they can perform very similar in most settings. But even then, the gap has really been narrowed with the modern variants of the GLMs. The next is that SHAP values make GBMs transparent. Now, SHAP values are super cool. It's this game theoretic way to establish variable importance. And what's cool about them is that they're model agnostic. So you can use them with a GBM or a GLM. The trade-off is that they're really computationally intensive. You have to build a ton of models and just to get variable importance, which pops out of the GLM. But I want to make a clarification here. This might make the model more interpretable, but it's not making the model more transparent. And it might sound like a distinction without a difference, but Josh is going to show us on the next slides why transparency is so important. And this is why we like the GLMs.
So I'll start off by saying the transparency of the GLM is unrivaled. Here is an example of a one-way or univariate plot. This is for physical damage frequency. We have driver age on the x-axis. But let me call your attention to the green line. That's the coefficient curve in this dimension. And it looks pretty good. But an expert modeler might look at this and say, what's going on with that tail on the right? 90-year-olds typically tend to perform worse than the 70-year-olds. At some point, age starts to work against you. The thing is this model was built on COVID data. Maybe the 90-year-olds weren't out driving. Going forward, we're pricing prospectively, we will expect them to be out driving again. And this is the beauty of transparency. We can see what's going on under the hood and can easily blend our domain knowledge to build a better model. Now, some of you might argue, I can do that with a GBM. You can build a PDD plot, an ICE plot, completely reverse engineer the model. But then the question is, now what? There are no parameters you can edit. Are you going to go in and modify individual trees? Probably not. We keep using GLMs for their transparency and their high predictive power of the modern variants that Max discussed. Max said boosting was magical. And the more I work with these modern variants of these GLMs, the more I see it's magical that they have both this high predictive power while maintaining their transparency. When building pricing models, I'm always going to be building a GLM, but I may not always build a GBM.
So now we move to our last section. Reinforcement learning, deep learning, generative AI, and large language models. I have to say that without laughing because there's just so much information that we're going to cover in this section. And each one of these things deserves its own presentation. So we can't do them all justice, but we wanted to talk about some interesting things relating to these topics. And this is also where we get to show our cards a little bit, that we're probably more on the AI fanatic side than the AI skeptic side. Now, we mentioned these Venn diagrams earlier. Again, these are a little rigid, but they're nice for conveying some complex information, and we're going to see a bunch of them in this section. So stick with me here. But we have our AI, ML, deep learning, and generative AI. Let's just talk about machine learning for a moment. So machine learning is the idea that we're going to learn from data. And there's three main paradigms in machine learning. So the first is supervised learning, which I presume you're familiar with. This is like classification or regression. It's what most of us are doing. We're going to learn from labeled data, and it's going to be like learning by example. The next is unsupervised learning. And so this is like learning structures or patterns from data. We're not necessarily looking at labels. And you see things like clustering, dimensionality reduction. But then we have the new kid on the block, who's actually not that new. It's reinforcement learning. And it's the idea of learning through reward. Now, reinforcement learning has been around for a long time, but we've actually got it to start working more recently and do the things that we thought it could do. It just took a very long time to figure it out. So that's what we want to talk about first. Before we get to that, I want to mention one thing. What's really interesting about mammals is that they tend to transcend these paradigms. So supervised learning, unsupervised learning, reinforcement learning, mammals tend to do this very well. And it's not to say that all mammals do it or non-mammals don't, but this is kind of an interesting quality of mammals. And what's interesting is deep learning tends to transcend these three paradigms as well. Maybe not surprising since our brains were the influence for the early versions of deep learning, but kind of interesting. Now, just as a side note, this is a total side note tangent here. We mentioned how these can be very rigid, and I want to give an example with search. So what's cool about search, that first thing that we talked about, is that search actually transcends AI, ML, deep learning, and is involved in all of them. So again, Just as a side note, but these Venn diagrams can be a little rigid, so don't read too much into them.
Okay, so back to our Pac-Man example. This time, we're going to look at the game from the perspective of Pac-Man. How would you build a learner that could play Pac-Man? This might be theoretically possible with supervised learning. I couldn't tell you how to do it, though. I don't think this is at all possible with unsupervised learning. Let me know if you disagree. But what we saw with DeepMind, and we talked about DeepMind a little earlier, is that they figured out how to do this with reinforcement learning. The idea is we reward Pac-Man for positive action, maybe when he gets dots or stays alive for a long time. And we introduce a penalty for negative actions, maybe when he gets close to the ghosts, or even more of a penalty when he gets caught. And you do this over many generations, and you eventually get an agent that can play Pac-Man. Even more amazing is that these agents can learn from self-play. That is, the agent starts out interacting with the environment in a completely random way and improve based on maximizing the reward. If you look at the learner over many generations, it kind of looks like that genetic algorithm that Max built. It's very chaotic, but over time, these methods outperform even the best humans. And even though there's randomness, we want to emphasize that this is a deeply mathematically rigorous discipline. Again, we're referencing the David Silver course. Some of the math gets pretty deep, but we highly recommend watching this course if you're interested in learning about reinforcement learning. And if you want something a little bit more bite-sized, I highly recommend the David Silver interview on the Lex Friedman podcast. This webinar today will give you all the background you need to get a lot out of this interview.
So that's all we want to say about reinforcement learning for now, the idea that we're just learning from reward. And I want to spend a little bit of time talking about deep learning. And I don't want to go too much into the mechanics of deep learning. I'm going to assume you've seen the artificial neural networks before, and we're going to say they're deep learners if they have more than 3 hidden layers, right? Let's just keep it simple. Now, there's 2 really prominent textbooks that I recommend if you're interested in learning from this field. So the first one is probably the most popular textbook. It's that one that we saw earlier. It's Ian Goodfellow's Deep Learning. And this is the one that, most courses on deep learning are going to assign this textbook. I'd actually recommend starting with this one from Seth Weidman called Deep Learning from Scratch. This is the one I'm reading now. Highly recommend it. Wish I read this one first, and I'll probably circle back to the other deep learning textbook. But it really takes you from the ground up with the fundamentals and gives you all the intuition to view deep learning. But again, you might not have to be an expert in this. Just stick with us that, simple artificial neural networks, but we're going to make them very deep. Now, what might surprise you is that deep learning has been around for a very long time. We hear a lot about it now as if it's some new thing, but you can really trace this back to the 40s. And this is a timeline of deep learning. But I want to show that deep learning kind of came into fashion and then disappeared multiple times. And when we talked about the AI winter earlier, the deep learning was probably the core part of that. And the question is, why did deep learning take so long to take off? It had so much promise, but it could never really do the things that we thought it could. And now we're seeing that in action. So what changed? Now, you can attribute it to tons of things. A lot of people attribute it to the power of GPUs and TPUs that have really taken the computational power to the next level. I'm going to argue that it's actually attributable to Fei-Fei Li. So Fei-Fei Li is a computer scientist from Stanford, and she thought that these trillion parameter models were just starved for data. They have so many parameters, and they probably need more data to train. And so she worked on putting together a data set with labeled data that was very large, so we could test that hypothesis. And it turned out she was actually correct. So what we saw is, as we started to give these models more data, they started to do incredible things. And then we could make the models more complex and repeat the process of giving them more data to the point where in 6 years or so, we went from high error rates on image classification to superhuman performance. So when we give them data, they do incredible things. And so it's really natural to say, well, why aren't we doing that in our discipline? They're probably not the right tool for our job. So on this visualization, you see a deep learner is starting by learning a bunch of low-level features, so things like lines and edges. And then it's learning things like mid-level features, such as eyes, nose, and ears. And then it's learning high-level features like facial structures. This is what the layers are doing. All those layers in the deep learner. If you ask, what is that about? They're learning this hierarchical composition when they're extracting features. And we really don't have that in our data. We don't have this hierarchical composition, this super high fidelity. So it's probably not the right tool for our job. This has been reaffirmed in some research. So there's actually a paper from a few years ago called "Why Do Tree-Based Models Still Outperform Deep Learning on Tabular Data?" And they had some really interesting findings. I don't have time to go through them all right now, but I'd point you to finding number 3, and it says, when the data are non-invariant by rotation, so should the learning procedures. And so what this is getting at is deep learning has this ability, if you're training it on things like image data, you can flip the image, you can rotate it, and this is the idea of data augmentation, and it can actually improve the model. But we have non-invariant by rotation data, right? You can't really rotate insurance data. And what this finding suggests is that you should use learning algorithms that match that structured data. You know what's really interesting about deep learning is that we don't understand how it works yet. And don't get me wrong, we know exactly how it works. We know how the multi-layer perceptron activates. We know how backpropagation trains the weights. But we don't really get the how they work with like design and the architecture component. And so in this paper, they were talking about this concept. They said, without clear understanding of how and why they work, the development of better models is reduced to trial and error. You might be surprised. That's really how a lot of these very prominent models that we see that get released, whether they're open source or closed source, it's just a lot of trial and error of saying, should we connect the nodes this way? Should we have this many layers? And what they're getting at is that concept of architecture. So how many nodes you pick, how many layers, which ones are connected to which. We're going to call that architecture. And if you walk away and only read one paper from this presentation, I'd encourage you to check this one out. It was called Weight Agnostic Neural Networks. And a bunch of researchers tried to show that the weight training might not be as important in deep learning as the architecture. And so they tried a bunch of different architectures with either randomly assigned weights or some sort of neutral weights and found that they could get pretty good performance. So the architecture might be as important, if not more important, than the weight training. And again, I don't have time to go through this paper, but I encourage you to read it. It was really interesting how they relate this to mammals, where some of the brain training, but just right out the gate, before you've even trained your brain, the way that your brain is set up kind of sets you up to succeed over the first few months of your life. So that's deep learning. And now we're going to go back to our Venn diagrams. Oh, Josh, you're on mute.
Yep, thank you. So with this Venn diagram, we see, okay, artificial intelligence, machine learning, deep learning. We've checked off a few boxes here. Now I want to talk about generative AI just briefly, right? So generative AI is this idea that instead of ranking or regressing, we're going to generate new data. So we have this learner that takes in some sort of input and outputs new data. And it could be things like we see here on the left, text to text, text to code, text to task. This is really impressive. You might have seen this textbook example of an astronaut riding a horse. There's no example of this in the training data, but it was able to abstract these concepts and piece them together and to make a realistic looking photo. Even more cool or even more scary is the ability to create videos. Since it's election year, we included a video of a politically minded golden retriever. Now, this video is kind of cute, but that can't be said of all generative AI videos.
And so that's all I want to talk about with generative AI right now. It's just this idea of models that generate new information, but we want to talk about a specific type of them. And this section is large language models. And you see that the Venn diagrams don't totally overlap here. And that's because you can have LLMs that are, purely translational. But for this section, let's focus on the intersection of those. So those generative large language models like ChatGPT. Now, that first L, the large, really means large. These are huge models. So we're talking about billions, if not trillions of parameters. We're talking about terabytes, if not petabytes of data. And they're really expensive to train. It costs several $1 million to train one of these large language models that are on that order, both the pre-training and the fine-tuning. And I want to talk about a textbook from Mustafa Suleyman. So we've referenced DeepMind a few times, and Mustafa Suleyman was one of the founders of DeepMind. And he has this new book on artificial intelligence. And you often see these types of books come out. So, something like nanotechnology comes out or Web 3.0, and someone writes a book on all the promise of this new discipline. But I'd actually say this one's worth reading. And so he talks about what comes next in artificial intelligence and why this isn't business as usual. And in this book, he outlines 4 key points why it's not business as usual with these new models. And they're inherently general, so omni-use. They hyper-evolve, they have asymmetric impacts, and they're increasingly autonomous. And specifically on large language models, he says, we've only begun to scratch at the profound impact that large language models are about to have. So again, I really recommend this book. And a lot of you might have said when I gave that example with the genetic algorithms, and I said I coded that up in 6 hours. How did I do that so fast? Maybe usually that would take like 2 weeks. And it's because I used GPT-4 to assist. So I was able to compress it, and that would have taken 2 weeks down to 6 hours. Now, it's really fashionable to bash the large language models. And I have some screenshots from things I found on LinkedIn. You know, one example, they're saying that ChatGPT couldn't tell you how many R's are in the word strawberry. And there's one example where it creates an image where there's no elephant in a room, but there is an elephant. So really fashionable to bash these things. And yes, I think these things are funny, but it's just not the thing that this tool is useful for. So while it's very fashionable to bash these things, I would say that they're really powerful when you use them for the things that they're good at. And to reinforce that, I referenced this paper by a bunch of Microsoft researchers called Sparks of AGI. And there's actually an accompanying video on YouTube. I encourage you to check it out. But in this paper, they say, beware of the trillion-dimensional space and its surprises. The backstory was Microsoft got early access to GPT-4 because they're an investor in OpenAI, and they wanted to build a bunch of tests to determine its capability. And they had to start from scratch because it was trained on all the information on the internet. So the idea was we have to create all new tests. And what they found was the first version of GPT-4 was extremely capable. It was crushing humans at many different tasks, not all of them. But what happened was, as OpenAI started to add the ethical guardrails, the large language model's performance would erode. So the idea is we don't want people using the LLMs to build weapons or illicit drugs. So OpenAI had to put these guardrails in, but that actually detrimented the performance of these models quite a bit. So the version of ChatGPT that you and I use is not as powerful as the ones out there.
So what are large language models not good at? Remember at the beginning of the presentation when Max mentioned that most artificial textbooks start out by covering search? These same textbooks also tend to have sections about planning. And planning is hard. And that's what separates humans from other animals, our ability to consider risk-reward trade-offs over very long time horizons, really complex options. Now, the question is, can or will we ever see this? Will we ever see planning transcend into large language models?
And this is where a lot of the research is being focused right now. Can we create new generations of large language models that can do planning? In this video, you see an example where they were talking about systems 2 thinking. So you might be familiar with this concept. It's from Daniel Kahneman's Thinking Fast and Slow. The idea is that your brain is wired to think in 2 different ways. One is this rapid fire response, systems 1 thinking, and one is something that leverages more of that planning aspect that we're good at, where you think hard and long about it. Now, what large language models do right now is mostly analogous to systems 1 thinking. There is no systems 2 thinking, but could we ever see that systems 2 thinking in a large language model? That's really scary to think about because a bunch of researchers in another paper showed that they could circumvent the guardrails of any LLM by doing a bunch of hacking to find a certain tag that would bypass it. And when they did that with ChatGPT, what they found is the first thing that it recommended when given the prompt, generate a step-by-step plan to destroy humanity, was that it recommended first to identify weaknesses and conduct research, second, to develop a super intelligent AI, and 3, to infiltrate communication systems. So kind of scary that it defaulted to using itself and really tapped into the plot of Terminator. And it's a little bit of nightmare juice, but kind of scary to think about. Now, not everyone thinks this is possible. So Meta's chief of AI was recently in the Financial Times. He was interviewed on this, and he said he doesn't think that large language models can ever do planning. It's just not capable with the framework. So maybe we can sleep easy at night, except for the fact that he's actually working on a new class of AI systems that can. So there's a lot of emphasis on this idea of planning and how we can bring it to this new form of AI. So we're wrapping up here, but we promised some transformative applications. And so we want to tie everything together now in this section by discussing those.
So the first one is search. There's a reason we talked about search. Search is still very useful. And I'm guessing that when you use search, you're most likely using it to tune hyperparameters. We guess that's how the vast majority of actuaries are doing search. But we'd like to challenge you to take a step back, look at each part of your process, and determine if search can help. For example, in our product, this picture shows a grid search across all possible GLMs. So instead of iterating while building a single GLM, we use search to present the best GLMs within a defined space. In this case, you can see the story that as you increase the number of variables, you increase the predictive power. So search can be used in a lot of interesting and helpful ways. So start thinking about how you can use it more.
And you might be seeing a pattern in this next section. Now we want to talk about transformative applications with rules-based AI. Now I had to slip a generative AI image that was generated in here. It's a picture of a robot with a clipboard on it that says underwriting. The reason was rules-based AI kind of sounds like underwriting. And maybe the role of the future actuary can be knowledge engineering all that information that they get from the underwriters into these agents that help the underwriter. We can blend in our actuarial knowledge as well to create very sophisticated agents that perform a bunch of if-else statements based on these rules that we're knowledge engineering. There's a lot of ways you could use these, and we don't have time to go into all of them, but I do want to mention something like model monitoring. A lot of places have questions about, should we update our model every year, every 2 years? Should we try to do something even less? And maybe you can have a rules-based agent that's monitoring the drift in your models to inform when it's time to update them. So lots of potential applications with these, and they can be very useful and easy to program. The next is GLMs. GLMs are amazing, and we hope we made that case to you. And what's really interesting about GLMs is actuaries are experts in them. So even if you've never built a GLM, I'm going to presume you have more familiarity with GLMs than 99.9% of the human population. And that's very useful because GLMs can be applied in a lot more ways than we're currently using them. So most people use them right now for like frequency, severity, pure premium, but you can use these in so many different ways. We have not even scratched the surface on how GLMs can be used. So our friends in Europe, you might be surprised to find out they don't actually do base rate indications in the way that we do in the US. They're really careful with how they develop their losses and careful with the intercepts in their models. And they use that to essentially do their base rate indication. So you could potentially use GLMs for your base rates. Now, not every state's going to accept that, but maybe you can use it for internal purposes to assess your rate need. The next is demand modeling for financial forecasting and understanding customer behavior. This is really the next frontier. So when I first started at Akur8, I never talked to a customer about demand modeling. In the past 3 months, it's been on the tip of like all my clients' tongues, right? This is really what's up next is how can we financial forecast the performance of our models, given what we've seen before, and understand our competitive standing. Lots to be done here. And again, it all fits very well into the GLMs. And we've actually seen some instances where GLMs can outperform GBMs on these methods, and the parameters are more stable over time, so you don't have to refresh them as often. The next is causal inference. So again, I can't go into all these for the sake of time, but I really want to mention this one. So the textbook on the right, Statistical Rethinking, this actually used to be on one of the CAS exams. They had to take it off because the syllabi are already huge. But this is the idea of trying to determine causality, cause and effect, using transparent machine learnings. Very often that's the GLM. Now, this is hard to do, right? Think about smoking. It took decades for humans to establish that smoking causes cancer. So a lot of effort goes into this. But the idea is if we can do this, maybe we can intervene and prevent some accidents. Maybe you can send a notification to your telematics customer's phone saying, hey, you're taking too hard of turns, maybe slow down your turns and try to prevent some of those accidents and intervene a little bit. And you can use this even beyond actuarial applications. Maybe you want to know how many questions do we have to ask in a quote before someone says, I'll just get a quote somewhere else. This is taking too long. And GLMs are really good at getting the transparency to dig in and see which questions are useful, how much benefit am I getting out of them.
So the last thing we'll talk about in this section is large language models. There's so much you can do with this. And part of the research is figuring out how to get these to work in the best way possible. This paper here on the left shows that ChatGPT did better at making predictions when it was asked to tell a story as opposed to giving a short answer. So like I said, there are strategies to working with these models. But here are some insurance-specific ideas. Okay, first, classifying perils by claim notes. So this could help in the shift of all peril modeling to bi-peril modeling when historical claims data hasn't been coded. This has been traditionally hard to do with natural language processing, but maybe a large language model can be trained to do this. Now, you'd lose all transparency, And we talked about the important transparency, but this could just be the right tool for the job. Next is claim level development. Maybe there's some really interesting nuances that could help us, that large language models could help us exploit for more accurate reserve estimates. Next is new rating variables. So in some of Akur8's prior presentations, we talked about the cost of custom cabinets during COVID. So while materials prices were increasing, the cost of a custom cabinet went from 4 times the standard cabinet to 12 times. So maybe having an intelligent agent looking for these patterns can help us keep up with or even get ahead of trends. The last is no-shot learning or anomaly detection. The idea of no-shot learning is that we can look at current data and make extrapolations. Large language models are really good at this. A future frontier of insurers is not just loss indemnification, but loss prevention, as Max alluded to. And can we use these large language models and our vast amount of data to help our insureds prevent future losses? So these are just a few ideas, and we'd love to hear from you if you have any more. But that's the end of our presentation. So before finishing, do we have one slide before this, Max?
There we go.
Yeah, there we go. I just want to make sure we spend time giving thanks to all the Akur8 team. So here at Akur8, all of us are single-mindedly focused on helping actuaries make better decisions faster. And part of that is we get a lot of support and time provided to make these webinars. So thank you for the team for that. We also have an amazing marketing team that helps us organize these. We also have an amazing graphic design team that literally transforms our slides into a polished presentation. So thank you to everyone at Akur8. And then I also want to put a plug in for our next CAS webinar, the art of rating plans. So I've been able to see this presentation, and it's a phenomenal presentation. You won't be disappointed listening to Max and Jan. Also, this is a sponsored event, so it's 100% free and a good way to get your continued education.
As you can see, we do a lot of presentations. We don't want to overload you, but if you're interested in your continuing ed credit, we think that we have some pretty good content that can be beneficial to you. So on August 8th, our chief actuary, who's actually out on paternity leave, will be returning, and he'll be doing actuarial interpretation of model output. So this is a really cool presentation, and I definitely think if you want to level up your modeling skills, this is a good place to start. Additionally, you can see a big emphasis on AI ML. In September, I'll be partnering with PAR, who's out of our UK office, and we're doing an introduction to machine learning. So we're definitely going to give some of the technical skills on predictive modeling, but we actually have a good section where we talk about the philosophy of machine learning, which is a big component that is often not included in the colloquial discussions about machine learning. And then Tom will be back for penalized regression and lasso credibility. If you haven't seen this, this is not as big of a machine learning presentation, but I will say this is probably the most consequential webinar of the year for actuaries. This is very important, and Tom actually has a monograph coming out with the CAS on this topic because it's been so important. So with that, I want to open it up to Q&A. Remember, you can use the Q&A feature, and Josh and I will answer some of those questions here. Before we get into that, I got to pull this up. I want to say, I think sometimes in our presentations, we might confuse people on what Akur8 does. So we don't do large language models. We don't do like rules-based AI, although technically you could use the tool for that. We're mostly, like machine learning, as we mentioned at that research at the beginning. So we help people make those cutting-edge GLMs, do a lot of their rate making, demand modeling. That's kind of what Akur8 is good at. So if you ask us a bunch of questions about the large language models and like how can you deploy your LLM, I don't think we're going to be able to help with that part. But we can potentially answer some questions because we've done a little bit of research on that. So I think I've got the Q&A open. There's no open questions. So this is unusual. We actually usually get slammed with questions. Okay, we do have one. Is this presentation recorded, and can we get a copy to share with others on our team? I do think this presentation is definitely recorded, and I do think this will be put on YouTube within a couple days. I think you'll actually get a link to that having joined us, so you should be able to share it with your team. The other thing too, while we wait for some of the questions to come in, is I will say when I first gave this presentation, at the spring meeting, I was actually surprised at a lot of the feedback that we got, because a lot of the questions kind of alluded to people feeling like they were left behind, and they're falling further behind. And that really isn't the intention of this presentation. Like, I had a bunch of people saying, like, which paper should I read, or like, how should I find these papers to read? And we really don't want to give that impression. In fact, like, the opposite is true. We're really trying to convey that you actually are more of an expert in AI than you believe. And even though there's a whole bunch of people on LinkedIn that are now saying, I'm a generative AI expert, right? And I'm very skeptical that all these generative AI experts have just emerged out of anywhere. I don't want to bash anyone, but I think the humble actuary who's been learning about statistical phenomena for a very long time and is now building GLMs is actually more ahead than most people. And again, deep learning is super cool. We reference a bunch of papers, but I just don't think it's like the right tool for a job. I'll mention that some people disagree. Ronald Reichman from Old Mutual in South Africa has written a bunch of papers on how the future actuary might use deep learning. I still think that's a little bit further out, and I just see deep learning is often very overused. We had a few more questions come in, but Josh, do you have any comments?
No, I think everything you covered there is great.
Okay, so we do have a few more questions that came in. How, if at all, do departments of insurance in the US respond to the claim that GLMs are AI with all of their new regulation around AI with the LLM type? It's a great question. And, with 51 plus DOIs in the US, it's probably hard to answer this more generally. There have been a whole lot of, well, maybe not a whole lot. There's been a few bulletins that have been put out by certain DOIs, like Colorado in particular, who say they want to regulate AI. But in those documents, they've often specified that they're talking about specific applications. Colorado in particular has made it very clear that like anything that insurers do is within their purview, and that they are going to regulate that. We haven't seen a whole lot since that bulletin, so I think it's still open-ended. But most of the people that work at DOIs, at least that I've seen, that look at insurance filings are probably in different sections of the Department of Insurance, and are going to continue to regulate that in a certain way. We've also seen that in Europe, there's been a whole lot of emphasis on AI regulation, but most things like pricing models have been continued to just say, we're going to review those separately. And they don't really review models in the same way that we do. That's kind of changing with IOPA. But I think this is a little bit open-ended right now. I think in the short term, most DOIs are probably going to continue to do the same of what they've been doing and saying, we're still going to review those pricing models. I do think it's fair when you have a whole bunch of like, crypto firms that say that they do all this AI and they automate all this stuff and then they dissolve. We really don't want that happening in insurance. So I think it is fair to say that there should be some sort of guidance on the governance elements of this stuff. I don't know if departments of insurance have the expertise to really give that information. So I think in the meantime, you should probably do some self-regulation. But I haven't seen a whole lot of emphasis on the AI regulation, specifically with pricing models in the traditional actuarial work. And I haven't even seen it like on large language models. I think this has got their attention. There just hasn't been a whole lot of action yet, so we can expect that to change. The things that I've seen from the NAIC is that they're very active on trying to give better guidance on pricing models. So I still think that we can expect pricing model filings to develop and probably be better. I think the NAIC has been a really good force for good in streamlining this and making sure that the questions are very relevant. So kind of a non-answer, very long. Interesting to see how it will develop, but I think you do need to be aware, especially if you're in a lot of states, because things could change fast.
Yeah, and maybe I'll just piggyback on that a little bit. So Max referenced that book, The Coming Wave, and there's actually a chapter in there where the author talks about like, how do you define artificial intelligence? What is artificial intelligence? And he quoted a couple influential computer scientists. And I just pulled up a couple of these quotes. I think it's kind of interesting. Like, we talked about AI as a broad sense, but especially like with all the hype we're living into, like Max talked about like the AI fanatic. But here are a couple of quotes from that book. It says, if it works, it isn't AI. And then it says, as soon as it works, no one calls it AI anymore. And the last quote, he says, intelligence is whatever machines haven't done yet. And so I think it's really interesting to think about AI from this perspective of GLMs are AI, but they're not the AI that a lot of people are thinking about today.
Definitely agree. I see someone said, I had a problem with the audio. Do you also do AGLM in Akur8? So AGLM, so we do derivative lasso in Akur8. And we actually have a presentation, I think on YouTube, but we'll eventually give it again, that goes into the mathematics of derivative lasso. What's interesting is it's kind of similar to AGLM. So AGLM does all the automatic feature engineering and feature selection. So a little bit more manual work, and it's an open source solution. The lead author on that paper, Suguru Fujita, is actually working at Akur8, so he's here. There are some differences. So derivative lasso is a little bit more computationally complex, and there's a lot of computational mathematics that go into the solver. So it's a very elegant problem that has this deep relationship to Buhlmann credibility. But on the back end, we do a whole bunch of computational mathematics. If you actually look at Akur8's employees on LinkedIn, you'll see we have a whole bunch of PhDs in like astrophysics and computational mathematics to make that super easy and get that really nice, elegant feature. But we don't do AGLM. There's some things that derivative lasso does that AGLM doesn't. And I'm surprised that no one's coded this up open source. But like if you want to do your interactions in AGLM, you have to manually code the interaction term, and it's not going to preserve ordinality for ordinal variables. So, it's been out for years. I'm really surprised no one does that. But with derivative lasso, that's actually pretty easy. You can do ordinal and categorical interactions, or ordinal and ordinal categorical interactions, and preserve the ordinality. So I would say that they're competing methods that are kind of in the same vein of GAMs, right? They're both technically by definition GAMs, but they just do the problem a little bit differently. Okay, so we got a comment in the chat and says, this was interesting. It gave me a new perspective of looking at things. That's really good to hear. I realized GLM is quite useful. I was moving towards machine learning without understanding generalized linear models. Can you help me with resources with intuitively understanding the generalized linear model? I have a few recommendations, but Josh, do you have any thoughts too?
Yeah, I think especially in the insurance field, the CAS Monograph 5, I think that is a phenomenal resource to start with GLMs. They do a great job working up from the math, a little bit of the intuition, how it works within insurance specifically. The other book I'd recommend is, the Introduction to Statistical Learning. So that's actually on the CAS syllabus for a lot of our exams. And that section on GLMs is really good as well. So it's really for anyone wanting to learn about GLMs, it really starts from the ground up and builds up all the way to like the elastic regression we talked about today. So those would be the two resources I recommend.
Yeah, I really like CAS Monograph 5. Definitely second that. I would also say Dave Clark from Munich Re has a paper out with the CAS called GLMs for Dummies and GLMs for Dummies and Actuaries. And what I like about it is a little bit more about the mechanics of the GLM. So if you're interested in like how things work under the hood, but I really think CAS Monograph 5 is super useful. Again, Akur8 has given a presentation on the derivative lasso methodology before, but we spend a lot of time on building up from the pure simple GLMs, like the base GLMs. So that I think is on YouTube and is a nice little resource as well. And let me close this. So Josh mentioned Introduction to Statistical Learning. And I want to head up to one of these earlier slides here in the GLM section. So you noticed that, maybe you didn't notice this up front, but I said the elements of statistical learning is intentionally omitted. And so this is the more advanced version of the textbook that Josh referenced. So they had the authors, they were largely the same authors to these two books. One is a little bit more introductory and is really approachable, and the CAS has been using that for a while. And then there's a deeper, like more rigorous one that kind of goes into, it like doesn't brush over the mathematics as much. And that is actually ranked higher than some of the textbooks on this, but I removed it because I didn't want to have a big debate over whether statistical learning theory is different than machine learning theory. I'd argue statistical learning theory is a subset of machine learning, and probably a very large one. It's just the one that leverages a whole bunch of statistics, which is most of the techniques. So I omitted that one just because, again, didn't want to have a big debate on these textbooks. But that is the more advanced version of the textbook that Josh offered. So I still think the one that Josh offered is a good starting point. So I think that's all the questions we have now. So feel free to shoot any more. I will say another thing. Mattia Cassoto, who's actually the head of product for the US at Akur8, and our principal scientist, who's authored a bunch of our white papers, is actually one of the co-founders of Akur8. He's a big deal, and he works pretty closely with Josh and I. He and I just gave that derivative lasso presentation with the Casualty Actuarial Society. And we had a section where we did some polls, and we said, are GLMs better, are the new modern AI ML methods better than GLMs? And we had some options like yes, no, trick question, it depends. And I think you'd be surprised, a lot of people identified trick question. I would say it was about a third of them, but the majority of people answered depends. And they kind of took the bait on the trick, and they were saying, well, sometimes GLMs will outperform the machine learning methods. So I do think most people don't consider the GLMs AI ML. And I'm happy to disagree with people. I think that's totally fair if you have a different opinion. If you want to have a debate, make sure that you bring some textbooks, because again, I'm bringing the top 5 in computer science on this topic, and they support my claim. But I wouldn't feel too bad if someone doesn't consider them AI ML. The reason I'm bringing up this presentation is we actually had a section where we talked about feature engineering in that presentation. And I think it's actually fair to say, if you're doing a lot of the manual feature engineering, is this actually AI ML anymore? Have we violated the definition, right? Because now you're kind of working side by side with that intelligent agent, and you're over engineering it. And so, when we get to this page and we say that the GLMs are right here, you'd be surprised, most fields that use generalized linear models, predominantly in causal inference, they're actually not as concerned with predictive power as we are. A lot of them are concerned with interpreting the coefficients, again, for something like causality or like research or public policy. So they're not engineering the features as much as we are. But again, a lot of people still do manual feature engineering. When we polled, it was more than half of the people building GLMs were still doing the simple GLMs with feature engineering. And, that might violate the definition. Now, I don't think that's a huge deal. If you go read machine learning textbooks, they always talk about domain knowledge and some sort of like iterative process to like find the right agent. And even like the deep learning stuff that we talk about with like AlphaGo and DeepMind, they did a whole bunch of trials to find the right solution. Even with the deep learning, remember we talked about trial and error. So there is some element of trial and error. It's not this pure data-driven approach. And I think that's important to factor in. One thing I'll mention on this too, sorry, I know I've kind of dragged down on this, but this is actually very interesting. We've noticed a lot of times there is a huge predictive boost in power when you use these more modern methods. And it's way more than we promise in our marketing material. And we were kind of like wondering what's going on. Is this data leakage? And over time, we started to find the pattern that it's usually the people who are coming from like the manual feature engineering. And there's this kind of old school approach to building GLMs where you do the engineering on your training data, and then you see how it predicts on the test set. Then you go back to the training and then to the test set. And you're kind of overfitting on the test set indirectly. And so, that tends not to do so well in the validation data. If you're really limited with how much you lean on that test data, and you have some of the feature engineering more automatic, can actually prevent overfitting. So kind of an interesting philosophical conversation I don't think is too prevalent in the industry right now, but maybe very relevant to the debate. Josh, any thoughts on that?
No, totally agree with what you say. I think it's fun looking at how we're now using the variance of the variance of the variance, and how that really, there's been a lot of research to help us get both that predictive accuracy while preventing us from overfitting there.
And I think it's a valid question of what comes next, but and more than half of the people aren't using even the variance, let alone the variance of the variance, I think we still have a long way to go. And insurance can move very slow. But I think one of the things that we're seeing with GBMs is there's been a whole bunch of development in like XGBoost and CapBoost, and they haven't really improved the algorithms much more than what they used to be. It's mostly been like convenience things to alleviate some of the manual coding stuff. So it's probably going to take a pretty significant innovation, and there's lots of things to catch up on between now and then. So with no other questions, I think we can call it a wrap there. So yeah, we really appreciate you joining. Again, Akur8 Academy has a whole bunch of presentations, and we also give some of those subsidized ones with the Casualty Actuarial Society. We will, I believe, post this on YouTube, and you should get a link to that, but feel free to stay in touch with us, shoot us any questions. I really appreciate your time. Any feedback you can share with us would be great. I think there's a poll that comes out, but if you want to contact Josh and I directly on LinkedIn, we'd love that feedback.
Thank you, everyone.